Module 2 is Pablo Garcia. Pablo is currently an associate professor at the Department of Electrical, Computer and System Engineering at the University of Oviedo. Nowadays, he's focused on power converters, working as the connection interface of renewable energy and storage systems to the electrical grid. Pablo, gonna pass that on to you now.
Yeah, thank you very much, Michael. I will take control then. Well, now I cannot. Okay. Before it was showing the control, but now I cannot have control over the slides.
You can just let me know then when to pass them on.
I cannot do it. I don't know if Marian, you need to do something. Before it was shown the control, but now it's not.
Okay.
Maybe you need to make your screen bigger and the window with the presentation.
No, it's pretty large now.
Just let me know when you need the next slide.
I don't know.
No, I just seen the I cannot do nothing. I don't know. I mean, I don't know if I need to.
Just let me know when you need, and I will do that for you. I will.
Yeah.
pass
Okay.
it.
Okay. Perfect.
Yeah.
Then.
Mm-hmm.
So yes, if you saw the slides, that would be great.
We are sharing the slides. I can see them.
A moment. It's coming now. I mean, it's probably a connection, and now I can take control. Yeah, something.
Perfect.
Okay. Thank you very much then for the nice introduction. So I will then present a brief review about what we are doing in Module 2 regarding the modular battery system adaptable to different voltage levels. So basically, in here, the idea behind the works we are doing in Talent, okay, are that the fact that nowadays for the integration of energy storage to the grid, we are thinking all the time about the use of the energy storage coupled to the AC grid. The different solutions available in the market, thinking about consumers or applications for residential uses or even the buildings, they have a problem regarding the sizing of the energy storage. That's because of the, as you know, when you rise up the power in values near, that depends on the country, but obviously in all of those near the 10 kilowatts in power, you need to move to a three-phase system in the inverter side in order to deliver that energy from the inverter from the energy storage to the grid. You need a DC link, which normally it's in the rate of 700 to 800 volts. That means that in order to interface the battery, you need almost always, at least for this range of powers and energy, you need a DC-DC converter that is able to step up the voltage from the battery terminals to the DC link required, those 700 to 800 volts. However, what it happens is that many vendors, they offer solutions which are tailored in the range of dozens of volts for a single battery unit or module. That's, for example, the case of Cegasa, partner of the Talent project. If you try to make a DC-DC converter with such a huge step-up solution, it's not an easy task. Okay, it's something that is you need to do very special things, so special power converter topologies in there. And what do they nowadays in the market? In the market, what they do is basically to serialize, or either there are two alternatives which are shown on the right of the screen. Basically, the first one is to invest in a large module that obviously comes with a higher price. And the second one is to make a passive serialization of modules in order to increase the voltage in the overall positive and negative terminals, and then having a DC-DC converter which can be implemented using basic topologies for power conversion. The two solutions, they have a high price, okay, and even more important, in many occasions you end up with more energy than needed, okay, because the fact that you are making the investment in a large module or making the passive connection in series of the modules is just because of the needed voltage. It's not because you need to increase the energy, but you end up increasing the energy also, and that comes for a price. So basically, that's what we are targeting in the talent project in our implementation. We are looking for and searching for novel solutions in order to integrate those low voltage batteries, okay, in the range of dozens of volts, able to be integrated into the AC grid. That's the idea. And for that, this is what we named the IBAT. The IBAT at the very end is basically a power conversion scheme and a control system, which is coupled together with the battery, with a 48-volt battery in this case from Cegasa, and that we are able to generate a constant 400 volts DC. Okay, it doesn't matter that the battery voltage is varying with the state of charge condition. We keep that voltage constant. Okay, that is also a benefit in the terms of the power converter connected downstream in order to get the inversion, the AC integration. That power converter, okay, called the IBAT, it has some very special characteristics in the topology and in the control system that allows to make the parallelization and serialization of modules. Okay, and basically, if you need to have a large energy, then you can, and the system is the voltage is enough to be the 400 volts. You can actually connect those modules in parallel. Okay. And actually, they are designed so the systems can be connected and disconnected while operating. Okay, so basically, in the case in the parallel connection, in the case there is a failure in one of the IBAT modules, you can disconnect it, or it can be disconnected without compromising the others. The only thing is that obviously you lose that energy. And also, they can be connected in series. Okay, in series, even more. What you have on the battery side, let's say. It could be either a battery, it could be also, the control system is able also to implement a maximum power point tracking algorithm. So basically you can actually connect some PV panels, okay, or PV panels for that voltage range. I know it's low, we can actually increase to double. So basically we're in the range. How many modules you can stack in series? So far in the talent project in the University of Oviedo, we are doing the connection for reaching 1500 volts. Okay, for that, what we do is instead of generating the 400 volt per module, we reduce it to 375, and we stack together 4 of the modules. Okay, so basically with that we arrive to the low voltage limit, which is the 1500 volts. Even more, that connection or that architecture can be double, and that could be boosted up to the 3000 volts, basically, that they will need in the CEA, okay, for the integration of this solution for a large district level. The solution actually, because of the control system, it offers a sort of a flexibility regarding the independent operation of the energy modules. For example, it allows something that is impossible with the series connection of the modules. That is that the different modules, they can be operated at the same time, even in charging and discharging. Or actually, the power that each of the modules is given or to the grid or is absorbing from the grid, it could be different, completely asymmetrical. That's really important, okay, because for a series connection, because that allows, for example, that in the case one of the modules is having, for a reason, more aging, or it's having some problems, you can actually reduce the amount of power that module is given. Okay, and even though the voltage is kept constant in the output voltage, And if you do that, obviously, and we are working in the hot swap. Okay, in here is much difficult than in the case of the parallel connection, but we are working in that direction. So basically, if one of the modules get complete damage, that we are able to increase the boosting action of one of the converters to be able to provide that extra voltage without one of the modules. We are now still in the progress of doing that. Okay, it's just in simulation, but this is the path we are tracking. What we have inside of the control system in order to allow that modularity and to allow that multiple iPads can be coupled together is a concept that we proposed several years ago in the idea, that diagram. Then in Talent we are trying to develop the idea that is that we have what we call an intelligent power module, that it has that the power electronics, they don't have itself inside just the power switches and the drivers, okay, and the sensors, but also they have a control system which is actually implemented either per leg on the left, the half bridge configuration, or per full bridge configuration, okay? And those modules, they can actually be coupled together, okay, to a central control system, and it behaves with a given architecture, okay? The role of the modules in the power electronic architecture is actually planned or commanded by the central control system. So the modules can be working as a DC-DC converters, an inverter, as a multi-level converter. There are different configurations that the systems can be used. This is actually in the Talent project in the process to be patented. We have submitted a preliminary study of that approach, and we are now actually working in that direction. The implementation of these modules is implemented, the power switches is implemented with wide bandgap technologies. This is because of the run restriction that we have and because of the high switching frequencies we are targeting, and also the thermal stability. In here we are targeting switching frequencies in the range of 200 kilohertz, and for that we need to move to wide bandgap devices. In the case of the use of these modules for the energy storage, more precisely, we are using GaN for that implementation. The power converter, I mean, this is a schematic of what we have inside, and a prototype that is currently, I mean, has been already built. This is an old photograph. We are now testing that prototype, okay, and it's for the first version of the silicon version. The power converter inside the proposal, it allows to have isolation, okay, and it has a novel power converter topology, which is the three-phase dual active bridge, okay, with a different control system than the typical applied, in order to be able to operate with constant output voltage, even though the input voltage could be varying because of the state of charge of the battery. In here we have a comparison. This is obviously just valid for the case of the model from Cegasa. Different vendors, they will have different models and different results in this comparison. But this is on the left. What you have is the comparison with for the integration to generating at 800 volts bus with a pure passive solution from Cegasa, and with the IBAT. With the IBAT, basically what we need is two modules, the two in green, the so-called EBICs, okay? And for the case of the pure passive solution, you need to stack all of those, okay, just 70 modes in total. Obviously, the energy exists in there. They are quite large. This is not the, let's say, much realistic. It's completely realistic with the solution provided by Cegasa. Obviously, different vendors, they have different voltages in there, okay? But it's true that we have analyzed that, and normally what you end up, or in all the cases we have analyzed using the commercial solutions, is that we save around 25 of the energy need according to the IPAT implementation, and that translates to cost directly, okay? This is a cost comparison with the Talent solution and the four different commercial solutions. They are normalized, okay? So basically the normalization in there, obviously the lower the number, the better, okay? In the Talent solution, we are analyzing two different power topologies. That's why you see in there the single stage and the single stage 1C, which is means for the reduced power, okay? And as you can see, by the normalization, the saving in cost, the other one, the only one in here is this one, but this one has a lower energy than the modules that we have, okay? This is the only one that is in the range. The other solutions, I mean, they are far better than the far better, far worse than our solution. Okay, as a summary, probably here you have in bold. Okay, the reduction we are reaching is 30%. Okay, and for the 2C solution, that means double the power than the energy and near 40% for the 1C configuration. Basically, I think that's well. I think that was all. I don't know if yeah, that's all from my side. Okay, so thank you very much.
Perfect. Thank you very much, Pablo. Now, the second presentation in Module 2 will be delivered by Jeremy Martin. Jeremy has a background in electrical engineering. He's currently working at the Department of Solar Technologies of the CEA, where he is responsible for strategy in power converters activities. His areas of expertise are high and medium power converter topologies for railway traction and PV power plants. So, Jeremy, up to you.
Yes, thank you for the short introduction. Good morning, everybody. I will show you some slides about medium voltage conversions that we work on through the Talent project. So in this topic, we are working on a storage solution up to 3 kV, even if we can go up to 3.6 kV. Power is super as 3 megawatts, and the target is to own a utility scale power electronics building block. So as an introduction, it is the market around the renewable energy in 2050. As you can see, the annual market per year in 2050 is huge. There is 400 gigawatts forecast for solar installation, 250 gigawatts for battery, also wind, onshore and offshore, really big markets, electrolyzer, heat pumps, and system for transmission of energy. So we have to have in mind that all these systems use power electronics, and as the demand in power for each system is huge, high voltage consideration is on the table, because as you know, by example, if you do a parallel with railway traction application, from 1 or 2 megawatts you are already in medium voltage for reason of losses and cost also. Then next slide. I build a parallel of the topic which is dedicated to battery, but I did a parallel with PV because in PV there is research field on which we shift the voltage of the string, of the PV string, which in the history it was the PV string voltage was 600 volts, then it was 1 kV, and now it's 1.5 kV, and we shift to 3 kV PV strings because the trend is to install more power per string to have the highest power as possible per PV string. So there are research work on which we reinforce the insulation of PV modules. If you take the norms, you have to withstand 4 times the maximum voltage plus 2 kV, and so you get, by example, for 3 kV PV string, you have to insulate your module at 14 kV. So in the Talent project, it's the same approach. We boost the voltage of the battery to get a 3.2 kV battery. This battery is designed in the Talent project by the manufacturer Segasa and the University of Oviedo. They built an electronic battery which insulate. There is an insulation, in fact, in the converter, integrated at high frequency thanks to wide band gap semiconductor use. The topology has been selected, as well as the power module. I will have some slides after to show you more details. The power of the power electronic building block is around 3 megawatts. We can have an input voltage up to 3.6 kV, and the AC voltage can be around between 1.8 kV and 2.2 kV. The grid frequency can be 50 or 60 Hertz, that doesn't matter. The topology is an active NPC, and the peak efficiency targeted is 99%. This topology is based on an hybridization of silicon semiconductors and silicon carbide semiconductor in 3.3 kV blocking voltage. With this topology, you can work in inverter mode, so with a unity power factor or rectifier, of course, with a -1 power factor, or at 0 for support to the grid, like pure reactive power to the grid, or intermediate power factor. You can go to other power factor that is not unity or 0. So it is the availability of silicon carbide semiconductors in the market, and also in R&D. So for the talent project, we have decided to not go to power semiconductors that was already mature on the market, because in this blocking voltage you have already systems that are industrialized in mass production. So we consider it was too late. And for semiconductor with blocking voltage superior 3.3 kV, we see that is not mature yet. You have simples that are really expensive, but for industrialization, it's not really suitable to use this kind of blocking voltage. Even it's really interesting to use from a technological point of view. 3.3 kV now there are not yet in mass production, but there are shifting more and more in mass production. So we have selected this blocking voltage for silicon carbide module. We have identified 4 suppliers for this technology, which are Wolfspeed in the United States, Infineon in Germany, Mitsubishi in Japan, and Hitachi in Japan also. And for reasons of availability, we have decided to work with Mitsubishi power modules. So concerning the topology, we go to 3-level topology. As you know, we can use NPC topology, which is the standard topology 1, using diode clumping to the neutral point. It has the inconvenience to use long switching loop that decrease the dynamic performances of the converter, because you increase parasitic inductor. And we for rectifier mode especially, we didn't go to this solution because of losing of performances on the power electronic blocks. So we have selected NPC topology, which is called active NPC, when the diodes clamps to the neutral point are replaced by active switch, in our case SiC MOSFETs. So in inverter mode and in rectifier mode, you use only short switching loops, which is an optimization of using the semiconductors. Another point is we have decided to build a converter with 2-level standard modules associated to build a 3-level topology, so that for industrialization it's easier, because you have double sourcing. I have already said it, but you have only small commutation loops, and you mix silicon and silicon carbide modules. So it is a more detailed view of the power electronic building block. So you can use a battery up to 3.6 kV. The power is 3 megawatts. The semiconductors that are connected on the poles on the battery are made of silicon carbide and switch at the switching frequency. It's this reference for Mitsubishi that has been selected. And for the semiconductors that are connected to the output, to the phase, to the line of the grid, it's IGBT modules with the same packaging as the SiC modules and operating at 50 Hertz. So it is a simulation of the topology connected to the grid. In the Talent project, we build a model of the converter, including the possibility to set active and reactive power with the synchronization to the grid, and the injection of the third harmonic that allow to step up the RMS voltage, so to increase the power of the converter in the certain site, and also starting control to load the DC link and to increase the voltage and to start. There is some the result of simulation work on the project. So in the first step, we close the grid to increase the DC voltage of the capacitor. We charge the DC bus, and then we disconnect the resistor, the pre-charge resistor, and we inject 3 megawatts to the grid with 0 reactive power, and then we absorb 3 megawatts from the grid with also 0 reactive power. It is efficiency curve we have simulated by electrothermal simulation at several switching frequency on the SiC MOSFETs from 1 kilohertz to 3 kilohertz, and you can see that very high efficiency on the semiconductor side can be reached, superior as 99% from power from a few 0.5 megawatts, 3 megawatts. So we can expect good performances with this topology. We are now in Talent in a prototyping phase when we will experiment inverter legs.
Jeremy, I'm really sorry.
Yes.
Can I please ask you to wrap up so we have a few minutes for the Q&A as well?
Yeah, yes. I have finished my presentation. So if you have questions, don't hesitate to ask. Thank you for your attention.
Perfect. Thank you so much. Okay, so let's move to the Q&A session now. Please ask your questions in the chat if you haven't already. Maria, would you like to take over?
Thank you, Egle. Thank you to both presenters. Thank you to Pablo and Jeremy for your presentations. I don't see right now any questions on the chat, but well, I have, at least from my own, a couple of them. The first one is addressed to Pablo. Which, in your opinion, are the market trends regarding the energy storage in the low voltage distribution networks?
Okay, thank you, Mariam. I mean, in my opinion, the The idea, well, something Igor has said something also in that direction in his presentation. At the very end, that we need that in order to get the price down and the solutions to be affordable, we need some things regarding the regulation, obviously, and that means that at the very end, energy storage is you are paid by the services, ancillary services given to the DNO in the case of integration of the low voltage distribution networks, and for the case of the manufacturers of energy storage solutions. At the very end, one of the trends would be that the integration of those systems should be as quick as possible, as seamless as possible into the grid, and that means that the interoperability in there is the key word for that integration. So and for that we need is that to be in agreement in a standard in the communications for the DNO integration. We need that the energy storage, they are tailored for the solutions. That means the energy and the voltage required in the market in those grids, and that means that at the very end that you have references provided in your offer, in your commercial offer, that can be integrated with the fewer components as possible to the required voltage levels. Okay, but remember is at the very end having a DC link for three-phase systems in the range of 700 to 800 volts. That's the in my opinion the trends in there.
Thanks a lot, Pablo, for your answer.
Welcome.
And now a quick one for Jeremy also. Can we consider a full IGBT high-performance power electronics solution to accelerate the short-term industrialization of the technology? We cannot hear you, Jeremy.
I did cut my microphone. Now it's okay normally. Yeah. So the question is interesting because we see in for the medium voltage technology we prototype in talent, we mixed silicon carbide and silicon power modules. As in introduction, I showed that 3.3 kV silicon carbide modules go more and more in mass production, but it's not here. Now it's not here. So maybe we can see in this development, in this prototyping, two time scale, maybe one time scale which is short, with maybe an industrialization with a full silicon solution, and maybe later with an hybridization. But maybe the two possibilities are here, and of course we think we will go to higher performance because switching losses are much less than in IGBTs, because in IGBTs you have the more losses, and turn off you have the take current that creates a lot of dynamic losses, and especially in high voltage modules. So maybe yes, it could be there could exist two versions of medium voltage. What we can do at the CEA is to study the two possibilities, to have a clear view of what we can get from these two paths of designing the converter.
Okay, thank you, Jeremy. Thanks a lot for your answer.
Thank you, Marianne.
I think we can move on to the next module.
Okay, perfect. Thank you very much. So we're going to move to the last module of our workshop today. Our first speakers for the module, we will have two speakers for the first presentation. First one is Daria Skirt. Daria has a background in mathematics. She currently works as the project management and technical coordinator at Cybergrid, where she plays an active role in the research and innovation technology department, focusing on the topics of battery energy storage systems and virtual power plants. And our second speaker is David Boraya. David has a background in automation and industrial electronics engineering. He currently works for Siemens Gamesa Renewable Energies, and he is in charge of the company's off-grid hybrid plant controller. and the Lapland hybrid facility controller control algorithms. So David and Daria, the floor is yours now.
Hi, thank you. I really appreciate the opportunity to present you some of the development. Development we're doing within the Talent project. We just jumped to the slide with the architecture, but first I'd like to tell you what exactly this is, or what we're developing. It's the interoperable software to manage different hybrid and decentralized energy systems that are integrated into the grid. And the aim is what we've heard today many times, the promotion of the battery integration into the power grid, and thus also facilitation of the integration of different distributed assets, especially renewables, and consequently the flexibility of the energy system is increased. So on this slide, you can see our solution architecture, where the main parts are the virtual power plant, which is also called VPP, and the distributed hybridized energy management system, shortly called DAGMS. The virtual power plant and the cloud part of the DAGMS are presented in the middle of the picture, and both are located in the cloud. And there are also local DAGMS controls that are installed locally at each asset. And all these components are communicating efficiently to make use of the flexibility of the distributed assets. And to the system, we can connect different assets, loads, generators, and storage systems. The virtual power plant and the energy management system calculate a set point for each client. So the local DAGMS knows the schedule of each local asset, and then this is communicated with the cloud part. The virtual power plant gets the TSO and energy market data, which is presented on the left side of the picture. In our case, this will be simulated, and the set point for each is calculated then for each client as set. With such aggregation of several local assets, we can benefit from the flexible energy by using the energy storage and shifting some loads. There are many different clients that can be integrated and are depicted on the right side of the image. These are hybrid power plants, distributed energy resources, smart buildings, distribution network operators, and storage systems. And using such architecture, we can utilize and monetize their flexibility. And in the next slides, we'll present the main elements of this solution, the virtual power plant, the DAGMS, and the battery integration. The virtual power plant used in the Talent project is the flexibility aggregation platform provided by Cybergrid. And on the image, you can see the screenshot of this platform. Our virtual power plant has many different functionalities. The ones used in Talent are the aggregation of flexible assets, battery management, and market and TSO simulation. So in general, the virtual power plant can aggregate different flexible assets and optimize their performance when they're participating on the power market. This is either providing balancing services or trading on a wholesale market, like day-ahead, for example. On the image, we can see how the battery can be managed by the VPP, but instead of the battery, it could be any other asset presented on the previous slide. So the virtual power plant actually enables monitoring and overview of the asset. It tracks available capacity and sets the schedule of operation that is within the battery's capabilities. Aggregated resources can provide different services depending on their objectives and capabilities. And some can provide secondary control, others can participate on the day-ahead market, and some can do both. And another interesting thing, which is actually the key functionality being developed within the Talent project, is a digital twin of a stationary battery. And this is a digital replica of a physical stationary battery. It will enhance the existing virtual power plant and provide us valuable insights about the battery. While the real battery is connected to the virtual power plant, certain parameters are being monitored and evaluated, which gives us more insight on how the battery operates throughout its life cycle. Thus, the digital twin models and algorithms being developed within this project help us describe the behavior of the battery, its current state, and estimate the aging of the battery. And the digital twin can be also used to predict performance of the battery. For example, some operational modes can be tested, and in that way it is possible to optimize the usage and try to minimize the aging and the loss of the battery's capacity. And now David will continue by presenting the DHEMS. Thanks.
Many thanks, Daria. So I'm going to present the next element, which is the DHEMS. This figure shows the architecture already presented, where we can see the cloud DHEMS and the local DHEMS. Let's focus on the cloud DHEMS, that depending on the plant configuration, cloud DHEMS may be optional, because BPP is able to work directly with local controllers, but including a cloud DHEMS may mean some advantages. The cloud DHEMS works in collaboration with the virtual power plant in the cloud, by receiving set points and signals from it and transmitting that information to one or more local DHEMS, which is the responsible of the local control in a power generation menu. Cloud DHEMS may be connected to one or several plants managed by local DHEMS, such as smart buildings, battery energy storage system, distributed energy resources, and so on, the same way as the virtual power plant. Some of its main features are the internal database, automatized reports, and the list of supported communication protocols. In addition, cloud DHEMS is able to manage the reactive power of the users. On the other hand, we have the local DHEMS, which is in charge of the local power assets of each facility, and it is able to start, stop any asset and distribute the received plant set point between all assets, managing the local energetic dispatch. It's able to support different storage technologies. In fact, some of them have already been tested in real, such as vanadium redox flow batteries and lithium batteries. It also has its own local database, automated reports, and local SCADA. So next element in the control may be the battery energy storage system, which is also compatible with the Talent control architecture, and they can be managed in two ways. It can be connected directly to the virtual power plant controller, and it also can be connected to the virtual power plant through the cloud DHEMS and the local DHEMS, for example, inside a power facility. In this case, in the figure, the local DHEMS would be in charge of sending set points and commands to the battery controller. Regarding the interoperability and its behavior as a software as a service, this architecture is focused in interoperability and flexibility. Therefore, it can be used in a range of heterogeneous power generation menus. This feature will imply cost reductions in the grid power integration. To achieve that, Talent project uses standard communication protocols, such as Modbus TCP, IEC 104, OPC, and so on. This is software as a service. So, thanks to the already mentioned, users could avoid high initial costs during the commissioning of the system for licensing or maintenance, and they will get an efficient management of their energy system by only paying the subscription fee. Cybersecurity has not been forgotten in Talent, and all threats and risks of this architecture are being analyzed by cybersecurity experts inside this consortium. And last but not least, validation. The control architecture in Talent project will be validated at a real facility, the hybrid facility of La Plana, managed by Siemens Gamesa, which is composed by a wind turbine, a photovoltaic plant, vanadium redox flow battery, lithium battery, a diesel power plant, and also some loads to simulate any demand profile. Thanks to this big hybrid facility, we can simulate and test multiple combinations of several power facilities combination managed by some local DHEMS connected to the cloud and to control all of them from the virtual power plant control. So many thanks for your attention.
Perfect. Thank you so much, David and Daria, for your wonderful presentation. we will now move to the last speaker for today, and that is Jesus Garcia. Okay, there we go. So Jesus has 36 years of experience working in the energy sector, during which he has worked with practically all generation technologies. For the last 15 years, he has been working in Brussels and has a deep knowledge of the European context and the functioning of the EU main bodies with regard to the energy sector. Jesus, the floor is yours now.
Thank you very much. Let me thank the organizer for this invitation and the opportunity to transmit to you some of my learned lesson that has been done during my career. As you mentioned, I was working during 38 years in Iberdrola. That is a utility company, Spanish utility company, and I was involved in the development of some projects related to a smart grid and the smart transition. Other important issue that I want to transmit to you is that during these 38 years, when I began my career, the utilities are vertically integrated, and then I suffered, or I was involved during all this time from this vertical integration until the present liberalized market that you know are in the electricity sector. That has been a way very interesting, really exciting, and plenty of very opportunities, business opportunities and issues that I will can transmit in some way in my presentation. Please, next slide. One important issue in the concept that we are dealing with is the concept of interoperability. It's very people use usually this word. People is typically talking about, but sometimes are not enough clear what interoperability means, because there are plenty of different interchanges of opinions and many different conclusions about. Next, please. Then my presentation will enter in this 5 or 6 different issues, that key concepts, what it means interoperability, what are the smart grid concepts, and how interoperability is connected with the smart grid, what does mean network interoperability and smart grid concept, what is the European market consideration and grid infrastructure, in order to remind this. I think an important issue just to transmit to you is that during this time, that maybe many of you that are maybe younger than me, you are not fully aware about the tremendous importance and the tremendous effort that has been done in the electricity market to reach that. I remind, even still in some places happen that when a customer has a problem, they call the company telling, please, I have a problem in my, I have no power in my installation. And then the first question that the operator told you is that, could you check if your neighbor has light or has connection? Why? Because at that moment, nobody knows what the situation of a specific customer is. This is a very curious issue, but it's very true, because at that moment there are no potential. The only way that the company knows that something is happening is when a big failure around 50,000 people or something like this is affecting a zone because a transformer or a switch has been off, then because they are receiving many calls. And then at that moment, that is still no phone connection with the system, then the people, the company, utility company, need to check what is exactly the situation is. Immediately they call to the managing center and try to identify what the problem is. Later on, this was moving on in the term that somebody is calling, and then they identify the prefix of the phone, and then they are able to identify where the place is, and then can give any kind of information. But now, you know, the situation is completely different. Now, even I able to connect to my counter, I able to see what my consumption is, what is my power is, etc. And then you know that are, as Manuel described at the beginning, Manuel we must thank Manuel the tremendous effort that he's done during his career in the European Commission, because was one of the guarantees that this system is working now. Believe me. Please, next. Then there are two issues that need to be clearly identified when we talk about the issues of interconnection or interoperability. I keep up this definition from the IEEE, and then normally interconnection deals with equipment and function used to interconnect distribution energy sources, units with an area electric power system, distribution and transmission. This is interconnection, meaning that is a cable, something is connected physically, and then you could demonstrate that this is done. But interoperability, by the way, incorporate any additional issues that are the different multiple network system devices, application components that interchange not only a power connection, if not they interchange also information related to what the situation is. This means that there are two issues that are on board. That is IT, that is information technologies, that classifies like method or information exchange between the different, we can say, system that include fundamental classification of command control, monitor data, alerts, etc. And additionally, there are other issues that are affecting the IT, that are the issues related to operational, functional, management assets, infrastructure, specifically regulatory, and finally, pricing and market or security. Another important issue that are affecting the interoperability is the CT, is the communication technologies. That is with the effective path that are available to transfer that information. And you can see that appear very easy, that appear on a big amount of consideration related to that. Information technologies related to data and communication technology. Thank you. Then when we put all together, we reach I put that because it's very complex to find. People talk about interoperability, but normally confused with the concept of the smart grid. The smart grid join interconnection and interoperability, and the other important issue is the manageability of this and availability of the data. And then you could see, this is a source from EPRI, that how now, thanks to the tremendous improvement of the ITs and CTs, information technologies and communication technologies, now we are in a situation in which any kind of service provider is able to promote their services to different areas inside, from an electrical vehicle that you could see in the center of the cloud, from a cogeneration that is in the right side, or for example, a campus of commercial, or whichever system that are around, that the operation are controlled normally by utilities, TSO, DSOs. The distribution also is connected with this, and the market has also operated. And then in the right side, you could see how the distributed energy resources, that has been the big, we can say, revolution during these last 20, 30 years, because when we arrived to the company with 20 years, the company has no distributed energy resources. We have only power installation, big power installation, meaning hydro, meaning nuclear, meaning thermal, meaning whichever, but no small installation. Now, the situation that at that moment, I remind very well, because I beginning at the beginning of my professional life, I was working in R&D, and then I began to introduce a PV system. And PV system with 100 kilowatt was my first installation. I remind the jokes of my colleagues related that, do you want that we stop the nuclear because you are connecting the 100 kilowatt power system? And then this is many joking. Now people, nobody joke about the importance of this revolution and this introduction of renewable. Next, please. It is important to see that we have a kind of mess in this issue, that we need to manage all of them together to be able to identify the smart grid concept and the interoperability in between. Always think about interoperability is the mean in which smart grid is supported. Then the smart meter is one of the revolution, but there are their integration, the distributed energy resource integration, the active customer that has been deeply described and explained this morning by Manuel Sanchez, the active demand, electric vehicle, that are issues that are now nobody take care, but it's very relevant and important issue as a load, but also as a source of potential storage, the energy storage that are obviously an important part that I have seen many good information that has been described and presented along the discussion. The renewable integration, thinking that from low level renewable, that is PV system of few kilowatts, until a big amount of megawatt from wind power, of offshore, or whichever. Telecommunication, that is dealing with a very important issue that we mentioned before, the IT system integration, because one important issue to be mentioned here is that time ago, when we were discussing related to the IT system, the IT system are described or are used by the normal people are now allowing the full incorporation to the power sector. Why? Because this is so typical when you are connected in the computer. This is still an issue that need to be solved. That sometimes you have a problem of disconnection, or the internet is not working correctly. Okay, you disconnect, you reconnect, you try again. This could not be possible in the power sector. There's no be able to do that in a way, because in the moment that we are talking about power, mean that if we have a problem of an alarm, or we need to react immediately. And then, yes, it's true that we have protection, but the question is not that. It's just to be able to react in a good manner, with a good information technology system, with a communication technology adequately, but online in the term of time that is needed, no after that. And this is an important issue that we need to deal with, because this is the big difference between that we can say software as usual and software to be used in utilities. This is an important issue that needs to be transmitted to many people, because sometimes when the people say, okay, I connect in the cloud. Okay, yes, but you connect in the cloud with what kind of response? It's important issue that need to be dealt in order to be able to incorporate these issues in that. In fact, now, even if we have evolved tremendously, then sometimes when you try to connect to your meter, you have to wait for several seconds, if no minutes, sometimes in order to do it. Why? Because this issue is still pending to be solved. It's still pending to have a real solution in which you are able to connect directly with the customer. It's true that there are many manufacturers of meter are really incorporate a kind of way to connect directly with the meter. And you don't need to do through the commercial company, it's not directly. And then in this way, you are able to interact with it. In order to fulfill the requirement of the smart grid is targeted, like has been mentioned by Manuel, then this timing, this IT system integration need to be done fully incorporating and online in a way that could be managed correctly by the power system. Thank you. Next. Then it's important to show you what is the level of integration that we have now. This is a sort of from the Grid Plus project, but you could see that there are very levels. There are 5 different levels from the 5 that is a smart customers that are aware and are participating actively. The level 4 that is smart energy management, meaning that customer is connected with somewhere and with an aggregator, an ESCO, a retailer that is selling the energy, in which they are able to interact with them related to how they are managing the energy, how are sending energy, how are consuming energy, but in an online way that I told before. The level 3, that is the smart integration, meaning that renewable energy, distribution resources, electric vehicle, whichever. Suppose, for example, this issue related to the electric vehicle, that we are talking about millions of vehicles somewhere. How we are able to manage the storage of millions of vehicles in a city if we have not an online direct interoperability and interconnection at the level that is needed. If this is not done, we are not able to manage the energy in a correct way, in an online way. This is an important issue. If we go down, we will find the smart networks and processes. This is a tremendous effort that has been done by the 2 operators of the market, distribution and market operation, transmission operator. Why? Because the situation before is that so only big installations are we can say, connected and monitored by the companies. But now it has been incorporated almost to be the full installation has been monitored, controlled at low voltage, because at high voltage normally this is an issue that was done before, and the question is very important process that has been done by many companies that are still making in some of them. There are an issue that is progressing right now, but is still not finished. And then in the transmission network operation, this is a different issue because
I'm very sorry, Jesus. I'm going to ask you to start wrapping up if that's okay.
Okay. Then then I think the last one I think is finished. My comment related to that. Pass to the next slide. Okay. Then I want to remind you that there are two issues, two levels that need to be also considered. That is the free market and other is the regulated market. And this is very important because most of the issues are related to regulated. That we have been, for example, who is owners, the battery system, the storage system, etc., that need to be done. And this is strongly depending, next one, please, on the regulatory issues. And then this is a reminder of how complex is the system, you know, from generation plant, transmission line, primary substation, we have to obtain secondary substation, domestic customer, industrial customer, distribution. All this mess of system need to be connected through energy and through information. That is the main issue. Next, please. Then my conclusion next. This is the interoperability is an integral part of the smart grid. This remind this is we are unable to consider interoperability separated, but need to be done. The electricity distribution network must evolve to accommodate the growing penetration of distribution generation, renewable mainly, and incorporate more active demand management. The electricity grid are going to undergo a strong revolution from the liberalization market that is still pending to be done. The obligation to improve the energy efficiency is a must, and it's an issue that is on the table, that has been obtained in an important manner already. The innovation and new technologies are a key element in the electricity sector, and the developing of network future is really exciting, as an issue that we are dealing with. This project is and all the actors in the chair must be involved in this process, from customer to DSO. Next one, please. I think it's the last. Then interoperability is a key element, an integral part of the development, I insist, but pending of issues that are mentioned before, like telecommunication, like for example, narrowband PLC, prime, broadband PLC, integration of other existing technologies through Ethernet, etc. And the same issue happened with the improvement related to data concentration, counter, etc. And many issues are also need to be solved, like technologies in public and private domain, and the public network that meet performance requirement that I mentioned before related to the online answer, online response. And I think it's my last slide. Next. Well, this is some key issues, but I think are very evident that this is adaptation of operative. Well, it's true that we need to adapt many other additional issues related to training, education, working flexibility, etc. But I think this is you can read this, but this is only to call the attention related to that. And then this is a very important change, but it's challenging and it still some time to be reached. But don't forget that this is our target, this is our work, and we can do it. Thank you.
Thank you very much, Jesus. That was very interesting to hear and a very good note to end on. So we have a few minutes for some questions.
Thank you. Thank you, Egle. Thank you, Jesus, for this very interesting presentation.
Thank you.
We are a bit late, but at least I would like to address one question that I am seeing right now in the chat. This comes from Jeremy Martin, and I read, which kind of innovation in the future do you see for human-machine interface from the technological and software point of view? I guess this is addressed to Daria and David.
Yes, maybe I can answer. Well, this virtual plant concept is quite innovative, but in addition, hybrid plant controllers are not very common right now, but it's growing thanks to the combination of the mainly wind, sun, and batteries. And in the future, I see it including maybe hydrogen generation plants or maybe EV to grid connected to these hybrid plants and better local and cloud control strategies. Thanks to work everything as a virtual power plant.
Thanks a lot for your answer, David. And I would make a quick question to Jesus Martin, just to finalize, if no other questions arise, of course. My question is, which is the role of cybersecurity, or maybe we can say, how should we address cybersecurity when we are involving all the needed technology to ensure interoperability?
No. Thank you very much. Very interesting question and very relevant question. The problem is I have only 10 minutes and then I don't enter in this. This is a part of the definition that we have in Smart Grid. When you, because this is an issue that in the same manner that I mentioned before, that when you are connecting with a system in your computer and then you could have some kind of delays and need to be solved, in the concept of interoperability, the cybersecurity is a key issue, because obviously not only because you have some kind of hacker that could try to manage in your system. You know, some people that could try to connect or to falsificate information that is received by the customer, or in any case also related to the bank account, etc., etc. And then this is an issue that has been, at the beginning, was very complex to identify this, but is now a very specific, we can say, group that is addressing cybersecurity system. This is because now, in this moment, there are still pending to solve some kind of issues related to the connection to the customer. And then most of the customer could connect directly to the meter, but not able to take control about. And similarly, this has been controlled by the issue. You take a look in the Prime, we can say, solution. The Prime solution also incorporate a layer that has been done inside the layer that I showed you, related to cybersecurity, in which there are a kind of connection or interaction with the system using a system of blockchain in order to limit the potentialities of any kind of intrusion, because when you make this kind of solution through blockchain, mean there are 2 or 3 factors of security that need to be interacted, and not only with the company, it not between different other systems. Meaning that when somebody asks for something, they need to demonstrate to several places that is the correct people that is making the order, or is making the connection, or is making the information request. This is an issue that now, but let me to know that this is a very complex, probably issue that need to be solved in future. And in fact, the Commission has several programs that are addressing this issue.
Thanks a lot, Jesus, for your answer. Very interesting topic.
Thank you.
Okay, if we have no more questions, then I would just like to thank all of our speakers today. Once again, thank you very much for your very interesting presentations. I think we have all learned at least something today. So thank you very much for participating. And I will now pass the floor back to Marianne for some concluding remarks.
Thank you, Egle.
Thank you.
So I have prepared some conclusions from our presentations, but as we are very late, really, we are very behind of schedule, I will pass this quickly because in any way, all participants will get this presentation. So I will get straight to the closing remarks. Here, this is just to show you which has been our planning for the organization of these activities with our stakeholders. We have a couple of stakeholders groups. One of them is dealing with energy utilities, and the other one is dealing with power electronics and battery manufacturers. There are several members already there, but this is open, so you are invited, and we would be very glad if you decide to join us. And we started creating these groups in May, June this year. Then this our first activity with our stakeholders, this first online stakeholders workshop. Then the next activity will be the distribution of an online survey, which will be partially based on the speeches that you have already been watching today, the presentations from today, and other interesting topics which might be related. Then next year, we are planning to have our second online stakeholders workshop. We don't know yet which will be the definite date, but we will keep you all informed. And another online survey will come after this workshop also. And all this will be collected inside our stakeholders vision document, which will have a public version, and we will share it. Then This is the link through which you can register if you are interested in becoming one of our members of our stakeholders groups for both energy utilities and power electronics and battery manufacturers. As you will be getting this presentation, you will be able to check. Then this is a quick look at our website. You are, of course, invited to go there and have a look of everything that we are publishing. And we have tweets, we have publications, our newsletters. So please keep looking at it. And this is our view of what would stakeholders be getting in return from. You will be punctually informed about our activities. There can be workshops, as today, the surveys I mentioned, and we are also planning to make some interviews. We are not sure about the format. They can be recorded or maybe written, and of course, they will be also always disseminated via Talent website and via the social media. And this is it from my side. Thank you very much for being there, for your attention. Thank you. Thanks a lot.